also want to talk a little bit about exam 3. So looking at the schedule and the pacing, there are a couple of options for exam 3. I just want to kind of get it in your brains and see what it is we might end up in. I did go ahead and pop the new homework today. That's homework 12. Where you have to actually solve the triangles in the ambiguous case. We've got the two separate ones. And that also has some discussion of vectors. So we're going to be talking about vectors a little bit this week, which is this totally new topic. And that's what brings us to the kind of question about the exam. So if we wanted to, we could have exam 3 before the holiday week. And that has advantages. The plan right now is not to do that. But since we are where we are in the pacing, I think it's wise to talk about it. So exam 3 can take place 1 of 2 weeks. I know a lot of people travel, so this first option might not be advantageous for everybody, but we could do it next week. Before the break. Or we could do it after break. I think it would be the Friday of the week. And if we were to do it before break, it would probably be on, well, we could do it the Monday or the Wednesday. This would be up to you guys. So if we opted to do it on Monday, that would of course be a week from today, and it would cover all the material up through the ambiguous case of the ASS triangles. If we were to do it after break, then it's also going to have the new material from vectors on it. And so I wanted to kind of feel out what you guys wanted to do. I know that because a lot of us travel for break, these are usually not super high attendance days, and I don't want to destroy your travel plans, but I also know that after being away from mathematics for like 4 or 5 days, it's easy to forget a lot, and that could be really harmful in this case. So we're not going to make an ironclad decision right now, but just so I can get a feel, how many would be okay with taking the exam before the break? Yeah, it's okay. You can vote more than once. I just want to get a feel for how you guys feel about this. Okay, how many would be okay with taking the exam after the break? So it looks like we're going to do the exam after the break. This means there's going to be a little bit more content on the test and a lot more time to forget the material, right? That's the scary thing. So if we're going to do the exam after the break, I think I'm going to open up a separate kind of supplemental homework for you guys to play on over the Thanksgiving break, or a worksheet, something like that, because it's dangerous. It's very dangerous to put down the math for like 4 or 5 days and then come right back to a test. So for my planner people, Friday of the week after break, that's exam 3, most likely. I'll make a post to Canvas after I've looked at everything to make sure that everything's going to line up. But based on what you guys seem to want to do and where we are in the material right now, it looks like exam 3 will cover everything through section 7.5 and will take place on the Friday after we come back from the Thanksgiving holiday. Okay. So with that said, is there anything from the homework that we want to look at? I think I have homeworks 9 through 12 today. So is there anything in there that you've been working on? Can you take a quick look?
I think it was 17 and 19. Part of 19 I did get right, but I couldn't get it right.
And which homework set?
11.
17 and 19, that's what you wanted also? So 17, we're solving triangles, and 19, we're using the law of cosines to prove. Yeah, that's cool. Okay. Let's do 19 first. 19's a lot of fun. So we mentioned this when we introduced the law of cosines. Homework 11, problem 19. They want us to prove the Pythagorean theorem. So we're going to start with the law of cosines, inject into that the hypotheses of the Pythagorean theorem, and then see that the Pythagorean theorem falls out as a consequence. So you can start with whatever version of the law of cosines you want. I think it's one of those like master 8 kind of somewhat guided problems. So they have you starting with, so we begin with the law of cosines. And the form they ask you to write down there is the a squared on the left. So it's a squared equals b squared plus c squared minus 2bc times the cos of a. What are the hypotheses for the Pythagorean theorem? Pythagorean theorem says if da 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 da, then da 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 da. Right? What's the stuff after the if? You know, the Pythagorean theorem we've been using all semester, that a squared plus b squared equals c squared stuff. What are the necessary conditions for me to apply that? To what sort of triangles can I apply? Yeah, right triangle, right? So if we want to prove the Pythagorean theorem, we're going to assume that the triangle ABC is a right triangle. Now they walk you through this in steps. They want you to do it in a particular way. Oh no, really they don't. They don't. Yeah, the process for their solutions there is really just this, and then you plug in these hypotheses. So what do we mean? I'm assuming that this is a right triangle. It's not oblique, right? So I'm going to label this a little bit different than our normal convention. Normally we call C the right angle and little c the hypotenuse. But it's arbitrary. We can pick those labels however we want. So if I call that B, then this is little b. And we can call this C, and this is little c. So some of the things in this setup I know, some of them I don't, right? I have no idea what any of those side lengths are. These have to be arbitrary because I'm trying to prove a theorem that doesn't include knowing the side lengths already. But the one bit of thing I do know, since the triangle ABC is right, when I label it like this means A is 90 degrees, or pi over 2, right? So let's go ahead and plug that in. So with A equal to 90 degrees, we can plug into the law of cosines and see a squared equals b squared plus c squared minus 2bc times the cosine of 90 degrees. What's the cosine of 90 degrees? Pi over 2 is the radian form of 90 degrees, but what's the x-coordinate of the point up there? 0, 1, right? Yeah, so cosine of 90 degrees, this is 0. So this reduces to a squared equals b squared plus c squared, which for this triangle is the Pythagorean theorem, right? That's all. The square of the hypotenuse is equal to the sum of the squares of the two other sides. So that's all they wanted you to do. They wanted you to plug in 90 degrees into the law of cosines for that angle, and then see that what falls out is the Pythagorean theorem, right? That corrective term. We mentioned that when we looked at the law of cosines the very first time, that it's basically Pythagorean theorem with this little corrective term on the end to account for the fact that the triangle in general needed to be right. But if the triangle you're playing with is a right triangle, then the law of cosines just says what Pythagoras says. I think maybe the thing that makes this weird is that we're used to calling the hypotenuse C. And the form of the law of cosines that they chose to write down there isn't the one that has C squared on the left-hand side. But we've talked about that also, and if you wanted to in a different setting, and separate from this, you can convince yourself that this is the same thing as if you started with that other form of the law of cosines. This is now the cosine of C. So this is just changing that labeling convention. So now here if I plug in c equals 90 degrees, then this becomes c squared equals a squared plus b squared minus 2ab cos 90. Cos 90 is still 0, so this is c squared equals a squared plus b squared, which is what we're used to seeing, right? So the labels on an oblique triangle are arbitrary. Usually we pick little c to be the longest side length so that it lines up with what we're used to seeing in the case where the triangle happens to be right. But that's why we have three forms of the law of cosines, because you can label those things any way you want. And it still says the exact same thing. Questions on this? Let's look at the one where we're solving a triangle then. That's number 17. They say to solve the triangle, they want all the stuff. Homework 11 up to 17. They've given us a little bit of information. They've told us that little b is 64.8. I'm going to leave off the units, but we're measuring lengths here in kilometers. Little c is 72.5. And cap A is 129 degrees and 40 minutes, which is an annoying notation that we've tried to avoid, but I think we talked about this a little bit on Friday, how to convert from the degrees and minutes notation into decimal degrees. So 40 minutes, this is 40 minutes of arc. That dash notation stands for minutes of arc, which is like a really old-timey way to measure fractions of an angle rather than saying 129.35 degrees. They're giving that 0.35 as pieces of 1/60th of a degree. So the conversion factor here, 1 minute of arc, is 1/60th of a degree. So you could just say it's 1/60th degree. So 40 minutes of arc, I multiply it through this relationship by 40. 1 times 40 is 40, so I get 40 minutes of arc on the left. And over here I get 40 times 1/60 degrees. But this simplifies to 4/6, or 2/3. And if you want that as a decimal, it's 0.66666666 repeating. So as we work through this problem, because we want to work in degrees or radians, we really prefer radians, but here we have to work in degrees. We need to make sure we carry enough precision in that 129 degrees 40 minutes. So the angle A here is 129.66666 degrees. And I can call it 129.6 or 129.67 or 129.667. But I'm going to carry, I think, 4 sig figs through this, just to be really careful, because we know rounding errors, they like to compound. As you calculate with something that you rounded, with something that you rounded, with something that you rounded, you can get further and further from the exact value. So let me approximate this. Like that. This is more than enough precision. We'll be safe doing that. But now from here, it's like all the other law of cosines problems. So we're going to draw a triangle that has these stats. want to make sure we draw it in a way that doesn't assume that it's isosceles or right or anything like that. Maybe something like this. Our normal convention is that C is the longest side length, so down here this is 72.5 little b, so this would be the angle cap C. I can label this guy, which one's closer to 7. So the larger of those angles here, let's call A, it's 129.6666 degrees. And that makes this cap B, and that makes this little b, which is 64.8. Okay, that's everything we know. So should I use the law of sines or the law of cosines to start going after the missing pieces? I need little a, I need big C, and I need big B. Law of cosines, right? Because what I have here is an angle that's trapped between two known side lengths, and that's always the setup that leads to a law of cosines type thing. Which flavor of the law of cosines should I use? We've got those 3 different ways of writing that. One of them will be useful here. Yeah, the one that involves the cosine of A, because A is the angle I know. So I write little a squared equals little b squared plus little c squared minus 2 little b little c times the cos of big A. That's my law of cosines. And I plug in the bits I have. This is convenient because I have everything on the right-hand side, and I want the thing on the left-hand side. So B is 64.8, so this is 64.8 squared, plus C is 72.5, so this is 72.5 squared. And then I have to subtract off 2 copies of B times C times the cosine of A is the cos of 129.6666-ish degrees. I wouldn't do that calculation in my hand. I wouldn't do that calculation on paper. I would do that calculation in a calculator because these are unpleasant numbers. But the square of 64.8 is 4199.04. I'm going to leave that in here and add to it the square of 72.5. And that gives me 9,455.29. Minus 2 copies of, well, maybe let's go ahead and multiply these guys out. So that's 2 times 64.8 times 72.5. This is 9,396. Exactly, which is nice. Times here we have the cosine still of 129.6666 degrees. Is this positive or negative? It's negative, right? Because the angle there is between pi over 2 and 3 pi over 2. We're on the right half of the, from your perspective, the left half of the unit circle. So the x values here will be negative, the cosines will be negative, so I expect this to go up, right? Not to go down. It looks like we're subtracting, but really we're going to be adding. So we can ask our calculator for the cosine of 129.6666. Make sure we're in degree mode. If you enter that in radian mode, you'll get something very, very different. It is. It's like negative 0.63. So then I'll multiply that by the 9,396. And then I will subtract that from this, but it's a negative thing that I'm subtracting. So we end up calculating here. Here's that. Plus 5997.647159. So that's how those pieces shake out. And once we correct for the minus sign, we end up adding them. So I can't negate this. Add it to 945.19. And we end up with the square of A being somewhere around 15,400. So we take the square root of both sides. From here we get that A is approximately, we take the positive square root, 124.3098. Yeah, we can round it there. They only want us to round to a single decimal place, if I remember right. That's the precision requested. Round the answer to the side A. Oh, to the nearest whole number. Yeah, so we have way more precision than we need. So to the nearest whole number. A is just 124. So we can come back over here and label little a as 124. Good so far? Okay, how do we finish? I now have all three side lengths and one angle. What sort of situation does that put you in? Yeah, we could use the law of cosines if we wanted to. There's a way to use that to get angles once you have all three side lengths, right? If you're given all three side lengths and no angles, you have to use the law of cosines. But the law of sines is in a sense simpler. And so I would start now going after those missing angles using the law of sines. So the law of sines says the sine of A over A, sine cap A over little a, is the same as the sine of cap B over little b, is the same as the sine of cap C over little c. And we just use two of these at a time. So if I take sine A over A, that's the sine of 129.6866-ish degrees, divided by the length, little a, which we were told to round to the whole number 124, and set it equal to the sine of cap b, which I don't know, over little b, which I do know. And now I have an equation that I can solve for the sine of cap b, and that turns this into one of the equations of the sort that we've been working on in previous sections. So I'll multiply both sides by 64.8, calculate the sine of 129.666666, and then take the inverse sine of both sides. So if you're looking for the algebra, multiply both sides by 64.8. We still have everything else over here. And then divide by 124, and that will be the sine of big B. So I'll take the sine of 129, sine of 129.6666 degrees. Multiply that by 64.8, and divide the result by 124, and I get 0.402267, call it 0.4023. And then finally we can take the inverse sine of both sides. And that will give me B is approximately the inverse sine of 0.4023, which is about 23.72 degrees. I'm not sure where they wanted us to round the angles. Answers for angles to the nearest minute. Okay, so they want us to convert this back then into the degrees and minutes notation, and then round to the nearest minute. So let me give the next two sig figs here. Well, they're both zeros, so 720028, 700, we'll round it to the 29. After that is a 7. So I have to come back to this relation now to write the angle B in terms of degrees and minutes. So I think this might be a good moment to pause. Really, we have the whole problem here. We just have to repeat that process one more time to get the angle C. So questions on finding little a. We'll come to using the law of cosines to get the missing side length there. All clear with how we rounded. Questions on finding cap B using the law of sines? then let's put that back into this other notation. And then I think I'll leave finding cap C to you guys, because we do have to do some new stuff today. So if 1 minute of arc is 1 over 60 degrees, then I want to go from degrees here back to minutes of arc. I'd start maybe like this, say 60 minutes of arc. Is equal to 1 degree. Any military people here? People are big fans of shooting. MOA, right? From sighting on a rifle, minutes of arc, same thing. And now what I want to do is take this 23.720029 and write the fractional part, the decimal part, as a minute or so of arc. So B was 23.720029. First, we split off the decimal part from the whole number part. I want that 23 degrees, and then I want to say this is 23 degrees plus some number of minutes of arc. So that's 23 plus 0.07200029. And the 23 I'm going to hold on to. But this is the piece that I need to then go back and use this to convert into minutes. Now, if 1 degree is 60 minutes of arc, then I can multiply on both sides of this relationship by this number in order to find out how many minutes of arc this number is. Oh, there's an extra 0 here, I'm sorry. 0.720029. So let's multiply on both sides by 0.7220. So we'll have 0.720029 times 60, I'm using this, equals 0.720029 times 1. And over here, these are minutes of arc. And over here, these are degrees. This is the thing I want. So in other words, to go from degrees back to minutes of arc, just multiply by 60. And that's all we're doing. So I take this guy, and I get 42 minutes. 42.0174 minutes of arc equals 0.720029 degrees. So the angle B, bring it back down here, which was 23.720029 degrees, is 23 degrees and this many minutes. And they wanted us to round the minutes to the nearest whole number. So 23 degrees and 42 minutes. So the degrees, minutes, there's actually seconds of arc also. If you want to, you can break a minute down into 60 seconds, just like we do with the clock. It's an ancient notation. We don't really use it. It's kind of good practice in like this conversion factor stuff, but it's not the sort of thing I'm going to test you on. So if you hate this, I don't blame you. I hate it too. It's an old notation. You'll bump into it from time to time, maybe if you're reading an ancient physics textbook or something like that. But most of the world works in radians. We never work in degrees, and we certainly never work in degrees in minutes and seconds.
How do you know when to use which one? This is what they say in the homework, so I would have to submit it one way and submit it the other way, and then realize that.
I think if you read carefully, you'll see what it does say. So they say round the side length A to the nearest whole number, round B and C to the nearest minute. So if you read carefully, read patiently through the instructions, it'll make clear. But yeah, I agree that that's frustrating. I find myself working these problems in radians often, and then at the end I say, oh, they wanted this in degrees. That sucks. But then you just convert to the other one. So read the instructions really carefully. If you want to save yourself some time, do that before starting the problem. But yeah, if you find this frustrating, I don't blame you. I do too. Other questions on this? So last time, we had some fun poking at the ambiguous case. We had some fun kind of investigating what can happen if the only bits of information you're given about the triangle are an angle and two side lengths. Your book likes to call those SSA triangles because they're afraid of the profanity, but if you're looking for a way to remember it, this is the case that it's AS, angle, side, side. Because it's the case where we don't have all the information, or where we might seem to have all the information, but there's still more than one possibility. So we're returning to section 7.3. This is the angle side to side case. So someone tells you this angle, they tell you this side length, and they tell you this side length. This guy we don't know, these angles we don't know. And the way we were able to suss out what could happen was by thinking about this as being on a little hinge, and this as being able to rotate. If the side length little a is smaller than this height, then we know that there aren't going to be any triangles. There's no triangle that works like that. Because as that little leg a spins around, you'll never smack the bottom. If this is exactly the height of h, then you'll have one triangle, and it will be a right triangle. If a is a little bit longer than h, though, then it's possible then we can have two triangles. And the picture we looked at like that last time. And we saw how to determine which of these cases we're in. We did a few of those calculations. So I could have a triangle looking like this, but I could also have another triangle. Both of these have this same angle over here, cap A, have the same side length here, little b, and have the same side length here, little a. So what we want to do is, in this case where there's two triangles, we want to be able to find both of them, right? This chapter is all about solving triangles. Here we appear to have enough information to solve the triangle, and we do, it's just that it's not completely determined. From the information given, we could find potentially multiple triangles. So how do we find these guys? How do we solve both triangles in the ambiguous case? So if this side length is little b, then for the one triangle, I would call this angle big B, and for the other triangle, I would call this angle big B. Let me call this second one B prime, just so we don't confuse the two, because they're both playing the role of what we normally label as big B. Everybody good so far? So B prime, just to be ultra double mega clear, this angle in here, right? It's the interior angle for the second of the two triangles. The one triangle is this guy. The other triangle is this guy. Maybe I'll give him some color to help him stand out. So the outermost triangle that you see here, that's one of the triangles we're trying to solve. And then also this blue triangle. So one of these triangles, I'll leave C unlabeled up there. Of course, there's a C and a C prime too, right? Here's C, and then here would be C prime. But the trick is to find the B's. Once you have A and B, of course, you can get C using the fact that the interior angles sum to 180. And there's a nice relationship between B and B prime. I'm wondering if anybody can see it yet. So on Friday, I think I asked, let's think about this a little bit. What did we come up with? And that's the big thing. And the way to see that, let me come in here and label this as, say, theta. What do you notice about B prime and theta? Yeah, well, B and theta have to be the same. So because the little triangle on the right is isosceles. These two A's are the same A, right? This is that same piece just swinging through. Theta is equal to B. All right, this angle up here needn't be the same, but because these two side lengths are the same, this angle and this angle have to be the same. Okay. But also, B prime plus theta must be 180 degrees. Do we see that? There's a straight line right here. And if I rotate through B prime and then also through theta, I've come back to that straight line from which I started rotating. Do we all agree that this is a 180 degree rotation? Then B prime plus theta has to be 180 degrees. But we just said that because the triangle on the right is isosceles, theta is B. So B and B prime are complementary. B prime plus B is 180 degrees. This is the key to solving the ambiguous case. Do we feel like we understand why B and B prime are complementary? Okay. So let's actually do it. Let's take a look. Suppose I have a triangle where, so we're going to solve the triangle ABC, where little a is 54, little b is 62, and the angle A is 40 degrees. On Friday of last week, we justified that this does have a solution, right? There is a triangle like this. In fact, we were sure that there were two of them. We calculated that height, h, and we saw that that height was smaller than little a. So little a, this arm is going to come through and smack that triangle's base twice. So we need to find B and B prime. Each one of these corresponds to their own triangle. One looking like this, another one looking like this. Okay. In each of these guys, here is cap A, here's little a, here's cap B, here's little b. Oh, sorry, cap B over here, little b over here. So this would be C and little c. A I know is 54. Little b I know is 62, and a I know is 40 degrees. So if I just gave you this picture and said solve this triangle, what would you do? So here it's not the case that I have an angle between two known side lengths. I'm going to get this guy out of the way so we can use this space. But just keep in mind that we have a second triangle to solve. And it looks like this. I would think maybe starting with the law of sines to get cap B. Because sine A over A I know, little b I know. So if I use the law of sines, I can set that up as the sine of cap A over little a equals the sine of cap B over little b. And only one piece is missing from that. Cap A is 40 degrees, little a is 54. So this is the sine of 40 degrees over 54 equals the sine of b over little b is 62. And this is not terribly hard, just like the one we were doing over here. We're going to solve for sine of b and then take the inverse sine of both sides. So continuing this work here, we get 62 times the sine of 40 degrees divided by 54 equals the sine of b. Compute the left-hand side and then take the inverse sine of that. So I'll take the sine of 40 degrees, multiply by 62, and then divide by 54. That tells me that the sine of v is 0.73815. Yeah, we're around there, 8015. And now I can take the inverse sine of both sides. And that gives me that b is the inverse sine of 0.73815, approximately 47.56 degrees. And that makes intuitive sense also, if we think about it. In this case, b should be greater than 90 degrees. In this case, b should be less than 90 degrees. Now that we have b, period, we can solve for c. So we know also that the sine of a over little a is equal to the sine of c over little c. The sine of a over little a is still sine 40 degrees over 54. Little c I can plug in. Oh no, sorry. Here we were solving for b, right? But we didn't have little c. Okay, so we need to do something else before this. I'm sorry. Yeah, we're not quite ready for that. We're almost there. What do we do between here and finding the angle little c? I'm sorry, finding the side length little c. I have a triangle. I know two of the interior angles. Can I find the other one? Yeah, they have this sine to 180, right? And that's what I need in order to set up my law of sines for little c. So now, a plus b plus c has to equal 180 degrees. Interior angles, every triangle in the universe adds to 180. I know a and b. So 40 degrees plus 47.56 degrees plus c equals 180. So subtract that 87.56 from 180. And that gives me c as 92.44. And from here, we can set up the law of sines needed to calculate little c. So finally, sine a over little a equals sine c over little c. Sine a is the sine of 40 degrees. Little a is still 54. Sine of c is the sine of 92.44 degrees, and little c is the thing I'm after. So I'll calculate the sine of 40 degrees and divide that by 54. The left-hand side here is 0.11903. And over here, I just have the sine of 92.44 degrees divided by c. So I'll leave that as that for now. A handful of ways you can move from here. I think the fastest is probably to take the reciprocal of both sides and then multiply both sides by this. So in my calculator, I can with full precision take the reciprocal of this number by raising the answer to the negative first power. You get 84.009. And over here, the reciprocal of that is c over the sine of 92.44 degrees. You could also cross multiply. Right? Questions so far on the algebra? So that take reciprocal of both sides operation isn't something we use a whole lot, but it does work. And then from here, we multiply both sides by the sine of 92.44 degrees. So you get 84.009 times the sine of 92.44 degrees is equal to C. The sine of 92.44 degrees, positive or negative?
Positive?
Close to 1 or far from 1? What about your unit circle? Close to 1, right? So if 90 degrees is 1. So it's 92.44. This shouldn't be changing the value a whole lot. But a little bit smaller than 1, right? Just past 90 degrees. We've just started to come down. So I'll take this number, multiply by the sine of 92.44. And it goes down a tiny bit. It goes down to 83.933. Rounding to the third decimal place. So that's how we completely solve the one triangle. What about the other guy? What about this guy? So here's A, here's little b. Here's the angle B prime, and this angle C up here is going to be different too, so I'll call it C prime. The process is the same. Once I have B prime, I just run back through this law of sines jaunt to get little c and C prime. But how do I get little b, big B prime? Yeah. That was the thing we discovered a minute ago, right? So that B prime plus B is always 180. So we have B. If I want B prime, I just subtract B from 180. So first, B prime is 180 degrees minus big B. And big B is something that we were able to find over here using our law of sines. So big B, 47.56 degrees. So B prime is 180 degrees minus 47.56 degrees. And that is, I have to take a slow. 180 minus 47.56, 132.44. Does this make intuitive sense? Remember, we stopped and did a little intuition check after calculating B, and we're like, okay, this lines up with my picture, this lines up with what I expect. What about the value of B prime? Does that line up with my picture? Does that line up with what I expect? What is it we said about B and B prime? One should be acute, the other should be obtuse, right? B we expected to be acute because he comes from the triangle when he comes from kind of the first pitch, right? As that A length thing rotated through, we smacked over here, and that gave me this acute angle here. So we said we expected this to be less than 90 degrees. This guy we expected to be obtuse, and he is. So before I get rid of it, questions on solving the first of the two triangles, or why we had two triangles, how we knew to draw the two triangles, what the two triangles should look like, or how we labeled them, any of those. Cool. Okay. Then from here, it's just another copy of this. We do the same thing again. I'll get it started for you. Working on the B prime triangle. We have B prime. We have A. A here was 40 degrees. We have little b, this was 62. And we had little a. Little a is 54. So we've already got B prime. We need the side length little c. And we need the angle C prime. So we know that A is 40 degrees. We know that B prime is 132.44 degrees. How do I get C prime? Yeah, all these have to add up to 180, right? So the same way we got C in the other triangle, we'll use to get C prime here. So that's 180 minus 40 minus 132.44. So that's 140 minus 132.44 is like 7.66. Did I do that right? $7.56. Sorry. So that's C prime. In other words, this triangle very, very skinny up here, right? Now you have all three angles. You have two of the side lengths. We can solve for the third side length using the law of sines. Finally, we say sine A over A is, the missing side length here is little c, so we'll say sine big C over little c. We can take reciprocals on both sides, do that right away. And then multiply both sides by the sine of c, and you get that little a over sine of a times the sine of c is little c. And we can plug in the known quantities there. Little a was 54, and I'm going to divide that by the sine of a, which is 40 degrees. And then I multiply that by the sine of c. Sorry, I'm really sure you're writing c prime here, right? Because the triangle we're working with is a, c prime, b prime. The two other ends there. So c prime is 7.56, so I'll multiply this by the sine of 7.56 degrees. And that gives me 0.13156 as c. I'm sorry, no, that's just the sine of the c prime. So this was 54 over the sine of 40 degrees, almost there, times the sine of c prime, which was 7.56 degrees. That's 54 divided by the sine of 40 degrees times the sine of 7.56 degrees. So this is c, and that is 11.0526. And that's it. We now found both of the triangles in the ambiguous case. And the key, the thing that you have to remember, is that b prime and b sum to 180 degrees. So you can find cat b working the problem as though there was nothing wrong in the first place. You work the problem as though you didn't even know there was a second triangle. And along the way, you'll pick up that angle capital B. Then, after you solve that first triangle, you just go back and run through all those steps again, working with b prime, the angle together with b that sums to 180. There's one other thing I wanted to say, just a quick warning. If little a is super duper long, what happens here? So we didn't talk about this last time, and it's not something that's crucial right now. But imagine this extreme case, right, where this side length is unknown, but this side length is given. So here's a, here's little b, here's little a. Now as this guy rotates around, we'll still have one triangle when he smacks right here. But because he's so long that he doesn't hit over anywhere else down here as he rotates, we just have the one oblique triangle instead of the two. So there's actually an interval for little a. If little a is smaller than h, no triangles. If little a is exactly h, one triangle and it's right. If little a is bigger than h, sometimes two triangles, like we've been working here. Sometimes if little a is enormous compared to h, you still only end up with one triangle. And you'll see this falling out. In your law of sines, you'll end up with taking an inverse sine of something like bigger than one, something like that. You'll run into. But you won't see that right away, so please get started on the new homework that opened today. I made it through all the web assign extension requests before class, but if you need a little bit more time, don't be afraid to submit an extension request for the homeworks that have passed. This afternoon I have that meeting, so we will not have the 2 to 3 office hour, but I'll be back to my regular office hour schedule. That's it. Have a good afternoon.